It's my first time to address this group, and I'm really glad to be here. It's a good organization. It's promoting a very worthy cause. Moog CSA is a part of a large company that has quite a bit to do with the space program in various aspects. I'll focus mostly on what we're doing at CSA, but also a little bit about what the greater Moog company is doing. So here's a summary of my chart. I'll start out with some flight hardware that permeates some of the systems that are flown, satellites as well as rockets. And then I'll get into the ESPA and Cubesat delivery stages, which is kind of the focus of my talk. ESPA is the adapter that's been discussed quite a bit at this forum, and is quite a capable secondary payload adapter. Cubesat's a smaller version of that that's really made for Cubesats, and I'll talk about ways to use that adapter to get sat cubes to the moon and beyond. And then I'll just talk specifically about the Cubesat flight adapters that we've developed and to some extent flown, and in the other cases are preparing to fly. And I'll finish up with some details on Cubesat propulsion from Moog, a deployment sequencer that we've developed, and a few slides on SoftRide, which is a vibration and shock mitigation system that we've flown for whole spacecraft vibration mitigation. We've flown that on 30 missions to date. So this small satellite rideshare is an area that I've worked in for probably 15 years now, and I'm, as Bonnie might say, I'm passionate about this subject. So I'm really glad to meet more people that are involved in this area. I know some of you from previous conferences and programs, but I'm meeting more people here. This is great. So rideshare is kind of a subset of launches that are becoming more common now. Rideshare is really a good way to get Cubesats and other small sats on orbit because there's so much excess lift capacity on all these launches that the United States and other programs are doing. So starting in the 1990s, when CSA was a small business, we developed the ESPA ring and the SoftRide vibration isolation systems under SBIR programs to AFRL. And we built on those systems and carried them to commercial development to really develop infrastructure for the U.S. space community. And now as part of Moog, we were acquired 5 years ago at part of Moog Space and Defense Group. We are extending our capabilities, teaming with the other companies in Moog to include avionics, propulsion, and integrated payload delivery stages. So I'll start out with should I do speed? So I'll start out with a mission that many of you are familiar with that launched this year and is now in orbit around the moon. Moog has quite a bit of content on this satellite and the rocket that delivered it to orbit. The Minotaur 5 rocket had our SoftRide system mitigating the vibration environment of the solid rocket motors on this Peacekeeper-derived rocket, and we also have Moog cold gas thrusters on the rocket. On the upper right, several of these systems are all developed by Broadreach Engineering, which is a recent acquisition of Moog Space and Defense, including the avionics unit, the lasercom payload, and the valve driver unit. We've also got thrusters on this spacecraft from Moog ISP, the former AMPAC ISP in Niagara Falls, and latch valves from East Aurora, the home base for Moog Space and Defense. Here in Mountain View, we built the ground transport environmental control and data handling system that transported the satellite across the country. And that was our first time to get into that, but it was good working with the folks at Ames on getting that satellite ready to go. So now I'll talk a little bit about the ESPA ring. It's been mentioned several times in this forum. This is, we consider this our flagship adapter product. It actually got us into the payload adapter business about 15 years ago when we started the SBIR program in 1998, under which the ESPA ring was developed. ESPA is a secondary payload adapter that gets inserted between the primary spacecraft and the launch vehicle. You can see right here where it fits in between the primary and the launch vehicle. The first launch was in 2007 on the STP-1 mission, carried 4 secondaries to orbit along with the Orbital Express primary satellite. Since then, it's been used for the LCROSS mission as a lunar impactor, and quite a few organizations around the country have developed it into an orbital maneuvering vehicle. Also, the Air Force Research Lab is flying it as a free flyer bus on the DSX program, which will launch on the Falcon Heavy in 2015 or so. That satellite's been ready to launch for several years, and it also has soft ride isolation on the components that are mounted to the ESPA ring. The full ring will fly as a satellite in medium Earth orbit to do experiments for the Air Force Research Lab. Here's an example of a extralunar orbit, I guess I'd call it. You can see what we proposed here with a team consisting of Space Dynamics Lab, Surrey Satellite US, Utah State, and Montana State Universities, was a proposed NASA mission to replace the LISA mission, which has been plagued by the high cost of the mission. It's probably a $2 billion mission to do the interferometry on orbit to measure gravitational waves. And we came up with a way to, what we thought, do that $2 billion mission for $400 million with a ESPA delivery system to take 6 microprobes to a very large triangular an orbit where the 6 satellites were forming an interferometer with the Earth at the center. The LISA program has a similar space-based interferometer, but it's in a trailing orbit to the Earth and much more difficult to implement. We did present this concept to JPL Team X, I believe it's called, who evaluates these types of things for NASA, and they thought we were too conservative or too unconservative in our approach. So we didn't get this one off the ground, but we spent quite a bit of time developing the capability to use the ESPA ring after it separates from its launch vehicle as a delivery system for these microprobes in orbit. And you can see in the image here that giant triangular interferometer is beyond the orbit of the moon, so you can see the moon in the image there. One of the ways we've developed to put CubeSats on the ESPA ring, and we've already seen a number of ways to do that, from planetary systems, canisterized spacecraft dispensers bolted to an ESPA port, or other ways to mount CubeSats on the ring. But this was a way to do it with no concerns for the coupled loads analysis, because we qualified it to the very strict requirements of the NASA Launch Services Program at Kennedy, so that their requirement was to carry the 2 P-pods on an ESPA port with the modes of that particular space payload being above 100 hertz. So it was totally out of the coupled loads region. We developed it with actually the minimum frequency of 120 hertz, so we're well out of that coupled loads region. And we can carry secondary CubeSats, or might be called tertiary, even while we're flying an ESPA payload. ESPA is made to carry 400-pound small satellites as secondaries, and while it's carrying up to a 20,000-pound primary. So after the primary separates, you can pop off these secondaries, you can release the ESPA ring and fly it as a free flyer delivery stage, and that's what we would like to do to get to a point where we can use this ring for delivery of CubeSats or other small sats. We've been kicking around ideas for CubeSat deliveries with ESPA and other adapters that we build. You saw yesterday in Jake Sikowski's presentation from ULA the idea of the Mule, which is a BUSIC collaboration with ULA and other small satellite organizations to use the ESPA ring with electric propulsion to take CubeSats to the moon or to Mars. That's a much grander vision than what I'm showing here, but we're just kicking around ideas internally because we have the capability with all of the Moog propulsion, avionics, and adapters. This is one of the concepts we've come up with, but we'll be glad to work with Busick on the mule concept and provide those types of delivery stages to for this community to get satellites to the moon. We've got another adapter called the Cubesat, which is similar to the NASA NLAS adapter that was presented yesterday. It's actually funded by some of the same sources. Steve Buckley at the Operationally Responsive Space at Kirtland Air Force Base was a real driver behind the original NLAS adapter. And then this is kind of a next generation NLAS adapter called Cubesat, developed by a small company in Albuquerque with Moog CSA as a team member. The first launch of this adapter will be next Tuesday out of Wallops in Virginia, with a stack that looks just like this image here, with 2 Cubesat adapters. Each has equivalent of 8 3U satellites. Some of those are 6Us, and a 250-pound satellite on top called STP-SAT-3. This launch goes on Tuesday, and I've just shown here quickly the test configuration, showing some mass simulators with the actual, these were the flight units that we did a protocol test on so that we could fly them. The NLAS adapters, Moog CSA was involved in that too. We worked with NASA Ames to finish off their design, and then we built it for them and tested it for them. Did static testing down at Kirtland Air Force Base, and as well as random vibration testing down there. And this is the mission that's been talked about several times here that'll launch next spring or summer out of Barking Sands at Kauai, with the University of Hawaii as the primary, and 13 Cubesat payloads. It's a similar form factor. We call this the wafer adapter configuration, similar adapter to the Cubesat. With the Moog capabilities, we've integrated propulsion into the wafer, just as we envisioned to do with the ESPA ring. This would be a smaller delivery stage where we could put the propulsion on one of these adapters. They're 38 inches in diameter and 10 inches tall, and then add Cubesat adapters that have Cubesats in them to deliver to various locations. It's just some examples of some of the calculations done on just the individual propulsive stage. The components listed on the left from the Moog, various Moog organizations, and then some calculations on specific impulse, and the delta V that can be achieved just with this little package here. But this is just a starting point, and we're looking forward to getting these going with the thrusters that have a lot of flight heritage from Moog ISP and Niagara Falls. A couple other of systems that we've been working with is Athena Commercial Rideshare. This is where Lockheed Martin and ATK are bringing back the Athena mission, the Athena rocket, to launch small satellites on a routine basis for commercial rideshare. We're also involved with Tricept, who's developing a ESPA payload type of container to containerize satellites from P-pods up to small ESPA class satellites that would go inside a box, and the box always weighs the same amount and always has its CG within a bounded spot in the middle to provide a box that looks the same to the payload stack no matter what's in there. So eventually we expect to fly these for missions where they care about changing satellites out quickly or shrouding them for security or competition-sensitive purposes. Moog's also looking at Cubesat propulsion with putting some of the Moog ISP type of thrusters onto Cubesats. A lot of people are doing this, and I think this is a very important part of the Cubesat world. It's not really accepted yet because of the idea of having hydrazine or other propellants in the mix while they're Cubesats are supposed to be pretty inert, but I think it's the future, and we'll all benefit from that. Moog cold gas propulsion is easily scaled to various sizes and these are some of the examples of some often used thrusters, and we are developing a deployment sequencer that we can integrate with our Phantom Ride box with any of our adapters to deploy the various payloads. Then quickly on soft ride, this is the mitigation of vibration environments during launch. We developed these in the 90s under SBIR to AFRL, and since then have flown on 30 missions, ranging from the very small Terrier improved Orion to the Delta IV Heavy. We've had 3 missions on the Delta IV Heavy and 2 to date on Falcon. We've got 2 coming up on Falcon 9 to launch a constellation of satellites on ESPA, but that'll also be soft ride isolated. The Minotaurs and the Tauruses are solid rocket motors, and they always need soft ride because of the rough ride on those solid rocket boosters. Recent launches have included the IRIS spacecraft, the LADI spacecraft, and the ORS OG2 spacecraft on the Falcon 9 CRS mission. We've got OCO 2 coming up, a couple of Falcon 9 missions, and we've delivered our first European system for a GEO Cubesat that will launch next year. I mentioned DSX already, and so in summary, we're looking forward to building flying ESPAs and flying wafers for delivery of CubeSats and other small sats. We've got a lot of flight heritage on some of these products already, and we expect to develop Moog propulsion and use other Moog entities to help us do this type of work and advance the cause here for lunar cubes. Thank you.
Thanks, Joe.